So the second question is asking you to look at the various criteria here in A through D and decide which one of them is not sufficient to prove that, that H is a subgroup. Right? And so you looked at option B and said, no, that's exactly the one-step test, right? If X and Y belong to H and XY inverse belongs to H, that's the one-step subgroup test for H. Same thing with D, just with the roles of X and Y interchanged, right? X inverse Y belongs to H. Also a subgroup test. And C looks like a two-step subgroup test, that if my set is closed under the operation and also closed under taking inverses, right, then that's the two-step subgroup test. And so by process of elimination, that only leaves A. But A looks awfully similar to what test? The finite subgroup test. So if we wanted to actually turn choice A into a legitimate subgroup test, what do I have to add to this? What else do we have to know to turns it into what we call the finite subgroup test? That H is a finite set. Right. Then we'd be in good shape. But if H is not a finite set, then just knowing that H is closed under the operation of the group is not sufficient to guarantee that H is a subgroup. If you were prove the proof down here using a two-step subgroup test, what are the two steps? What are the two things that you have to prove?
If you say just like
Closure.
That maybe X inverse. Yeah.
Closure and inverse.
So it's XY is an element of H.
Okay.
And then the X inverse.
Yeah.
Got it. Where are X and Y coming from?
Are all X and Y that are element of H.
Yeah. So we'll say let X and Y belonging to H be chosen arbitrarily. And my two steps are I need to show that XY belongs to H and also that X inverse belongs to H. Okay. So give me the argument for how do we know XY belongs to H? First of all, what is the price of membership in this subset? Having odd order. So how do we know that X times Y has odd order? That's our burden of proof now, right? Well, how do we know that's true? How did you make this argument? First of all, what do we know about X and Y themselves? They have odd order, right? Then X has odd order, Y has odd order. So let's call the order of these things. I don't know, what do you want to call their orders? Maybe, I don't know, K and L or something like that. And each of K and L are odd. Yeah?
Is it okay to define odd as n minus 1?
N minus 1? Maybe not.
Isn't it 2n
But 2n minus 1 I might agree with.
N could be like 3.
So yeah, if we want to, we could define this as 2n minus 1, 2m minus 1 for some integers n and m. Right? That's one way.
As like an even integer though, and then do it?
Yeah, but then you would probably just end up setting n equal to 2 times j or something, using the definition of even. So, all right, so let's say we do that, right? X and Y now have odd order, 2n minus 1, 2m minus 1. So how am I going to show that X times Y has odd order? How do you investigate the order of any element? What do you want to do with that element? Right. What I want to do is I want to show that there is an odd number that I can put here as a power on my xy that's going to give me identity. So where is this power going to come from? What power do I know I can raise xy to that will definitely give me the identity? 0, certainly. That's very true, right? If I put a 0 up there, I'm for sure going to get the identity. But we can't have 0 be the order of any element. Because if it could be the order of any element, it would be the order of every element. Because every element raised to 0 power is going to give me the identity. So besides 0, let's be super concrete about this. Let's suppose x has order 3 and y has order 5. Okay. What could I raise x times y to? What power could I take of it that I know is going to get me back to the identity? 15. Well, let's think about why that is, right? I'm multiplying xy by itself 15 times. But what else do we know about the operation in this group that we haven't used yet? Yeah, there's a key assumption in the statement of this problem. My group needs to be abelian in order to make this argument work. But because my group is abelian, what can I do to simplify this product? Move all my x's to the front, all my y's to the end. How many x's are there? How many y's? Why is this good news? If x has order 3 and y has order 5? Yeah, x to the 15th is just the 5th power of x to the 3rd. Y to the 15th is the 3rd power of y to the 5th. But what is x to the 3rd? It's the identity. What is y to the 5th? It's the identity. And so this is just the identity to the 5th times the identity to the 3rd, which is otherwise known as multiplying the identity by itself 8 times. I'm just going to get the identity. Okay. So what this proves for me is that the 15th power of xy gives me the identity. How do I know that that guarantees that xy has odd order? Because remember, order has two pieces, right? It's a power that gives me the identity, but it's the least such power that gives me the identity. How do I know that some smaller power of x times y is not going to give me the identity? And this is the point at which I asked myself, I don't remember whether this, did we prove this yet, or is this a part of chapter 4? But here's the giveaway, right? The giveaway is that if g to the power k is equal to the identity, then the order of g is not necessarily k, but the order of g is a factor of k. So in our example down here, the 15th power of xy gives me the identity. That means that the order of xy is a factor of what? The order of xy divides 15. But what do I know about the divisors of 15? All the divisors of 15 are odd. Right? All the divisors of any odd number are odd. Right? And therefore, the order of xy is odd. So that's the kind of careful argument that if you're laying out a proof of this kind of thing that you would need to deploy. What is the argument for inverse, by the way? If I know the order of an element, what's the order of its inverse? The same. See if we can convince ourselves of that. Right? Me and my inverse are going to have the same order. Now, why would that be the case? So if x to the power k is equal to the identity, then what can I say about x inverse? Well, x inverse raised to what power is definitely going to be equal to the identity, according to this? Well, if I put a negative 1 inside there as a power, then I can put a minus k on the outside, and I'm still going to have something that's logically equivalent to this last thing. Right? So the minus kth power of the inverse of x is equal to the identity. But then all I have to do is multiply the left-hand side of this equation and the right-hand side of this equation by x inverse to the power k. And when I do that, I get on the right-hand side the kth power of x inverse. On the left-hand side, I have the identity. So the kth power of the inverse is going to be equal to the identity. Therefore, the order is going to be a factor of k. We can also make the argument that if the order of this is any less than k, then that would mean the order of x ends up being less than k, which is not true, and therefore we can make the conclusion. So me and my inverse are always going to have the same order as one another. And therefore, if the order of x is odd, the order of the inverse of x is odd, and therefore the second of our two steps and the two-step subgroup test are satisfied.